Close your eyes for a moment and think about time. Not the time on your clock or your phone, but the experience of time itself. That strange sensation of moments flowing past you, carrying you from what was into what will be. Time is perhaps the most intimate and yet most mysterious dimension of our existence. We live inside it, we measure our lives by it, and yet when we try to grasp what it truly is, it slips through our fingers like water through a sieve. Tonight, we're embarking on a journey through two landscapes where time reveals its most bewildering faces. First, we'll venture into the vast cosmic theater where Einstein showed us that time itself can stretch and compress, where clocks tick at different rates depending on how fast you're moving or how deep you are in a gravitational well. Then, we'll turn inward to explore the nightly theater of dreams, where time dances to an entirely different rhythm, where hours can compress into moments and moments can expand into eternities. What connects these two seemingly separate domains? Both challenge our everyday intuition about time's nature. Both force us to confront the reality that time is not the simple, universal metronome we might imagine it to be. And both suggest something profound about the relationship between observers and the time they experience. Whether you're approaching the event horizon of a black hole or drifting through the landscapes of REM sleep, time becomes something strange, something fluid, something that depends fundamentally on perspective and context. This is a story about relativity in its many forms. It's about how the fabric of the universe bends and warps. It's about how consciousness constructs experience across moments. It's about the profound mystery that, whether we're hurtling through space at relativistic velocities or lying still in our beds dreaming, time never quite behaves the way we expect it to. To understand how strange time can become, we need to go back to the early 20th century, to a time when the very foundations of physics were being shaken. Before Albert Einstein published his theory of special relativity in 1905, time was thought to be absolute. It flowed uniformly everywhere in the universe, indifferent to motion or matter. A second on Earth was a second on Mars, was a second in the farthest reaches of the cosmos. Time was the universal backdrop against which all events unfolded, unchanging and unchangeable. But Einstein saw something that others had missed. He started with a deceptively simple observation that had been confirmed by experiments. The speed of light in a vacuum is constant. It doesn't matter how fast you're moving toward or away from a light source, you'll always measure light traveling at the same speed, approximately 186,000 miles per second. This seems impossible at first. If you're driving toward an oncoming car, its speed relative to you is the sum of both your speeds. But light doesn't work that way. Whether you're racing toward a beam of light or fleeing from it, it always approaches you at exactly the same velocity. Einstein realized that for this to be true, something else had to give. If the speed of light is constant for all observers, regardless of their motion, then space and time themselves must be flexible. They must stretch and compress in just the right way to keep the speed of light constant. This led him to one of the most revolutionary ideas in the history of physics: time dilation. Time, Einstein showed, passes at different rates for observers moving at different velocities. Imagine twins, one staying on Earth, while the other boards a spacecraft capable of traveling at 95% the speed of light. The traveling twin embarks on a deep space mission, and by their own clock, they're gone for 10 years. But when they return to Earth and reunite with their sibling, they discover something shocking. The Earthbound twin has aged 32 years. Time literally passed more slowly for the traveler. This isn't an illusion or a trick of perception. It's a fundamental feature of reality confirmed by countless experiments. Clocks moving at high speeds genuinely tick more slowly than stationary ones. The mathematics behind this is elegant. The time dilation factor depends on velocity. At everyday speeds, the effect is negligibly small. A clock on an airplane flying across the country will lose only a few billionths of a second compared to a clock on the ground. But as objects approach the speed of light, the effects become dramatic. At 90% the speed of light, time passes at about half the rate for the moving observer compared to someone at rest. At 99% the speed of light, the difference becomes even more extreme. This has been verified not just theoretically, but experimentally. Particle accelerators routinely observe subatomic particles living far longer than they should because they're moving at such high velocities that time dilation extends their lifespans from the laboratory's perspective. Muons, unstable particles created when cosmic rays strike Earth's atmosphere, should decay long before reaching the surface. But because they're traveling at nearly the speed of light, time dilation means they live long enough to be detected at ground level. Their internal clocks are running slow. Even the GPS satellites orbiting Earth must account for relativistic effects. These satellites travel at about 8,700 miles per hour, and special relativity predicts their clocks should run about 7 microseconds slower per day than clocks on Earth's surface. Without correcting for this time dilation, GPS coordinates would drift by miles within just a few days. Every time you use GPS to navigate, you're depending on Einstein's equations being correct. But special relativity was just the beginning. Einstein spent the next decade developing an even more radical theory: general relativity. If special relativity showed that motion affects time, general relativity revealed that gravity does too. In 1915, Einstein published his field equations showing that mass and energy warp the very fabric of space-time. Massive objects create curves and dimples in this fabric, and other objects move along these curves. What we call gravity isn't really a force pulling objects together. It's the natural motion of objects following the curved paths through space-time created by mass and energy. And here's where things get even stranger. Where space-time is more curved, where gravity is stronger, time passes more slowly. A clock on the surface of Earth runs slightly slower than a clock in orbit, not because of the satellite's motion, but because Earth's mass warps space-time more intensely at the surface than it does higher up. The effect is tiny, but measurable with precise atomic clocks. At sea level, time progresses by about 1/1000th of a second less per year than at the summit of Mount Everest. This gravitational time dilation has been measured with exquisite precision. In 2010, physicists at the National Institute of Standards and Technology measured time dilation between two atomic clocks separated by just 33 centimeters, about 1 foot. Even over this tiny difference in height within Earth's gravitational field, the clocks ticked at measurably different rates. This means your head ages ever so slightly faster than your feet. The difference is incomprehensibly small, less than a trillionth of a second over a human lifetime, but it's real. Einstein's theories fundamentally changed our understanding of time. Time is not a river flowing uniformly through the universe. It's part of a four-dimensional fabric called space-time that can be stretched, compressed, and warped by motion and gravity. Time is relative. How fast it flows depends on where you are and how you're moving. Two events that are simultaneous for one observer might occur at different times for another observer moving differently. There is no universal now that spans the cosmos. The present moment is observer-dependent. This has profound implications. The universe doesn't have a single timeline. Instead, every observer carries their own personal timeline through space-time, and these timelines are woven together in a complex fabric where what counts as past, present, and future can differ depending on perspective. Time, Einstein taught us, is not what we thought it was. It's stranger, more flexible, more deeply intertwined with space and matter and motion than anyone had imagined. Let's delve deeper into gravitational time dilation, because this effect reveals just how intimately time and space are connected. Imagine space-time as a vast rubber sheet stretched taut. Now place a bowling ball on that sheet. The ball creates a depression, a curve in the fabric. The heavier the ball, the deeper the curve. This is essentially what mass does to space-time. Earth creates a dimple. The Sun creates a deeper one. Neutron stars create wells so steep they're almost pits. And black holes, as we'll see later, create such extreme warps that they essentially tear holes in the fabric itself. Now imagine placing marbles on this curved sheet. They don't move in straight lines. They roll along the curves created by the bowling ball, spiraling inward or orbiting around the depression. This is what we call gravity. It's not a mysterious force reaching across empty space to pull objects together. It's simply the natural consequence of objects following the curved paths through space-time created by mass and energy. But here's the crucial insight. Where space-time is curved, stretched, warped by mass, time itself is affected. The stronger the gravitational field, the more space-time is curved, and the more slowly time passes. This isn't a side effect or secondary phenomenon. It's built into the very geometry of reality. Time and space aren't separate things that happen to be affected by gravity. They're part of a unified four-dimensional structure that gravity fundamentally reshapes. General relativity predicts that massive objects create gravitational potential wells. The deeper you are in such a well, the more slowly your clock ticks relative to someone farther away from the massive object. This has been confirmed through numerous experiments and observations. In 1971, physicists Joseph Hafele and Richard Keating flew precise atomic clocks around the world on commercial airplanes and compared them to reference clocks left on the ground. When they brought the traveling clocks home, they found that the clocks had gained time relative to the stationary ones, exactly as general relativity predicted. The effect was tiny, measured in billionths of a second, but it was there. More recently, experiments have measured gravitational time dilation with extraordinary precision. Scientists have shown that two clocks separated by just a millimeter, about the width of a sharp pencil tip, tick at measurably different rates due to the infinitesimal difference in gravitational field strength across that tiny distance. These aren't thought experiments or theoretical predictions. These are real, measured effects happening in the universe around us all the time. Consider the situation of astronauts aboard the International Space Station. The station orbits about 250 miles above Earth's surface. Up there, gravity is slightly weaker than on the ground. General relativity predicts that clocks on the ISS should run about 4 microseconds faster per day than clocks on Earth due to gravitational time dilation. However, the station is also moving at about 17,500 miles per hour, and special relativity predicts that this motion should slow the station's clocks by about 7 microseconds per day. The net effect is that astronaut clocks run about 3 microseconds slower per day than Earth clocks. Astronaut Scott Kelly spent nearly a year aboard the ISS starting in 2015. When he returned to Earth, he had aged about 5 milliseconds less than he would have if he'd stayed on the ground. His twin brother Mark Kelly, who remained on Earth, aged imperceptibly more during that year. These aren't just curiosities for physicists. Gravitational time dilation is woven into the technology we use every day. The GPS satellite constellation provides a perfect example. Each GPS satellite carries extremely precise atomic clocks and constantly broadcasts its location and the time according to its clock. Your GPS receiver picks up signals from multiple satellites and uses the tiny time differences in when those signals arrive to calculate your position on Earth's surface. But for this to work with the accuracy we expect, those satellite clocks must account for both special and general relativistic effects. GPS satellites orbit at an altitude of about 12,500 miles, where Earth's gravitational field is weaker than at the surface. General relativity predicts their clocks should run about 45 microseconds faster per day than Earth-based clocks, but they're also moving at about 8,700 miles per hour, and special relativity predicts this motion should make their clocks run 7 microseconds slower per day. The combined effect is that GPS satellite clocks run about 38 microseconds faster per day than they would on Earth. 38 microseconds might not sound like much, but light travels about 1 foot in a nanosecond. So in 38 microseconds, light travels about 11,000 feet. If GPS didn't correct for relativistic effects, position errors would accumulate at a rate of about 7 miles per day. After just a week, your GPS would be useless, telling you you're miles from where you actually are. Every time you navigate using GPS, you're relying on equations Einstein wrote over a century ago that describe how time flows differently in different gravitational fields and at different velocities. The deeper you go into a gravitational field, the more extreme the time dilation becomes. On a neutron star, where gravity is so intense that a teaspoon of matter weighs as much as Mount Everest, time passes noticeably slower than it does far from the star. An astronaut hovering just above the surface of a neutron star for 1 hour would emerge to find that weeks or months had passed for observers far from the star. The stronger the gravity, the more dramatic the effect. This raises a fascinating question. What happens at the ultimate extreme? What happens to time in the strongest gravitational fields in the universe? To answer that, we need to venture to the edge of the possible, to places where space-time is so warped that it breaks the rules we thought governed reality. We need to talk about black holes. Imagine a star much more massive than our Sun reaching the end of its life. It has spent millions or billions of years fusing hydrogen into helium, helium into carbon, carbon into heavier elements, fighting a constant battle against its own gravity. But eventually, the fuel runs out. There's nothing left to fuse, nothing left to create the outward pressure that counterbalances the star's immense gravitational pull. In moments, the core collapses. If the star is massive enough, nothing can stop this collapse. The matter compresses into an infinitely small point of infinite density called a singularity, and around this singularity forms a boundary called the event horizon. This is a black hole. The event horizon is not a physical surface. It's a point of no return defined entirely by geometry. It's the distance from the singularity where space-time is curved so extremely that escape velocity equals the speed of light. Since nothing can travel faster than light, anything that crosses the event horizon can never get back out. Light itself, the fastest thing in the universe, cannot escape. Hence the name, black hole. It's a region of space-time from which nothing, not matter, not light, not information, can ever emerge. But the event horizon is also where gravitational time dilation reaches its most extreme expression. Let's imagine observing a clock falling toward a black hole from a safe distance away. As the clock falls deeper into the gravitational well, we see it tick more and more slowly. Its color shifts toward red as its light is stretched by the intense gravity. It grows dimmer as fewer and fewer photons manage to climb out of the gravitational well to reach our eyes. As it approaches the event horizon, the clock appears to almost freeze. Time, from our perspective as distant observers, seems to stop at the event horizon. According to an observer far from the black hole, nothing ever quite crosses the event horizon. Objects falling toward it slow down asymptotically, getting infinitely close but never quite reaching that boundary. They fade from view, dimming and red shifting until they become invisible, but from the outside observer's perspective, they remain forever frozen just above the event horizon. Time dilation has become infinite. This is why black holes were sometimes called frozen stars in the early days after their theoretical prediction. But now, consider the perspective of someone falling into the black hole. From their point of view, time passes normally. They don't experience any slowing or stopping of their clock. They fall toward the black hole, accelerating under its gravity, and in a finite amount of time, by their own watch, they cross the event horizon. They might not even notice the crossing. There's no bright line or boundary they can see. The event horizon is a point of no return defined by geometry, not by any local physical phenomenon they could detect as they pass through it. This is one of the most mind-bending aspects of relativity. From outside, an object never crosses the event horizon. Time stretches to infinity. But from the perspective of the falling object, the crossing happens in finite time. Both perspectives are equally valid. There's no privileged reference frame that gives the true answer. Reality itself is observer-dependent in a fundamental way. As the falling observer crosses the event horizon and plunges toward the singularity, something else strange happens. Looking back out toward the universe they left behind, they would see time in the outside universe appear to speed up. The closer they get to the event horizon, the more the outside universe appears to accelerate. At the horizon itself, they would theoretically see the entire future history of the outside universe flash before their eyes, all of infinity compressed into a finite moment. Of course, this is purely theoretical, because the intense tidal forces would destroy anything trying to make this observation, but it illustrates how dramatically different perspectives can be near a black hole. Tidal forces, by the way, are another consequence of the extreme space-time curvature near black holes. These aren't tides like ocean tides, though the principle is the same. They arise because gravity gets stronger as you get closer to the mass creating it. If you were falling feet first into a black hole, your feet would be closer to the singularity than your head, and they would experience stronger gravity. This difference in gravitational pull across your body would stretch you vertically while compressing you horizontally. Physicists call this spaghettification, and for stellar mass black holes, it would happen long before you reach the event horizon. You'd be torn apart, stretched into a thin stream of atoms spiraling into the void. For supermassive black holes, the kind found at the centers of galaxies, with masses millions or billions of times that of the Sun, the tidal forces are actually much weaker at the event horizon. This seems counterintuitive, but it's because the event horizon radius increases with mass, and tidal forces depend on how quickly gravity changes with distance. For a supermassive black hole, you could actually cross the event horizon without being torn apart by tides. You might not even realize you'd crossed the point of no return until you tried to turn around and found that all paths led inward toward the singularity. Some theoretical models suggest that rotating black holes might create even stranger effects. A rotating black hole drags space-time around with it in a phenomenon called frame dragging. Inside a certain region called the ergosphere, space-time itself is being pulled around the black hole faster than light, and anything in the ergosphere must move in the direction of the black hole's rotation. Some solutions to Einstein's equations suggest that inside a rotating black hole, the usual causal structure might break down. There might exist closed time-like curves, paths through space-time that loop back on themselves, potentially allowing backward time travel. The physics here becomes deeply speculative and controversial, but the mathematics of general relativity at least allows for such possibilities. The movie Interstellar dramatized these effects beautifully, showing astronauts visiting a planet in orbit around a massive rotating black hole. On the planet's surface, deep in the black hole's gravitational well, time was dilated so severely that 1 hour on the planet equaled 7 years back on Earth. While the science was simplified for the movie, physicist Kip Thorne, who consulted on the film, ensured the basic concepts were accurate. Such extreme time dilation really could occur near a supermassive black hole. Black holes represent the ultimate extremes of what Einstein's equations predict. They're places where space-time is so warped that time itself can essentially stop, at least from the perspective of outside observers. They're laboratories where the fabric of reality is stretched to its breaking point, where our intuitions about time and space and causality cease to apply in anything like their familiar forms. They're cosmic time machines, where you could theoretically travel to the distant future simply by hovering near the event horizon and then returning to the rest of the universe. And yet, as strange as relativistic time dilation is, there's another realm where time behaves just as mysteriously. Not in the vast reaches of space, but in the intimate theater of the human mind. Every night when you close your eyes and drift into sleep, time begins to flow differently. In dreams, hours can seem like minutes, and minutes can stretch into hours. The brain creates its own temporal landscape, and the rules governing time there are as peculiar as anything Einstein discovered. Let's turn our attention inward now, to the sleeping brain and the enigma of dream time. Sleep is one of the most universal yet least understood aspects of human experience. We spend roughly a third of our lives asleep, cycling through various stages of consciousness, and yet the function and nature of sleep remain deeply mysterious for most of human history. People knew that dreams occurred during sleep, vivid experiences that seemed to unfold with their own logic and timeline, but there was no way to study them objectively. Dreams were private, subjective events that left no physical trace. Everything changed in 1953 when two researchers at the University of Chicago, Eugene Aserinsky and Nathaniel Kleitman, made a discovery that would transform the study of sleep and dreams. They were observing sleeping infants and noticed periods where the baby's eyes moved rapidly beneath their closed eyelids, separated by periods of quiescence. Intrigued, they extended their observations to adults and found the same pattern. During certain periods of sleep, The eyes darted back and forth in what they called rapid eye movements. They called this rapid eye movement sleep, or REM sleep. When they woke people during these periods of rapid eye movement, about 85 to 90% reported vivid, narrative dreams. When they woke people during other stages of sleep, dream reports were far less frequent and less vivid. This correlation between REM sleep and dreaming was strong enough that for decades, REM sleep was effectively treated as synonymous with dreaming. Here, finally, was an objective physiological marker that could predict when someone was likely to be dreaming. REM sleep turned out to have a distinctive profile that made it fascinating from a neuroscience perspective. Electroencephalogram recordings showed that during REM sleep, the brain's electrical activity looked remarkably similar to wakefulness. Fast, low amplitude, desynchronized brainwaves resembling the alert, waking brain appeared. And yet the person was deeply asleep, disconnected from the external environment. Muscle tone throughout the body essentially disappeared, a state called atonia, preventing the sleeper from acting out their dreams. Only the respiratory muscles and the muscles controlling eye movements remained active. This state is sometimes called paradoxical sleep precisely because of this contradiction. The brain appears active and awake based on its electrical signature, but the person is unconscious and paralyzed. It's as if the brain has disconnected itself from both external inputs and motor outputs, running internal simulations without the ability to sense or affect the outside world. Energy use in the brain during REM sleep equals or even exceeds energy use during wakefulness. The brain is working hard during REM, burning glucose and oxygen at remarkable rates, and yet all this activity is turned inward. REM sleep occurs in cycles throughout the night, alternating with stages of non-rapid eye movement sleep, or NREM. NREM sleep itself has multiple stages, from light sleep, where you can be easily awakened, to deep, slow wave sleep, characterized by large, synchronized delta waves in the EEG. A typical night sleep cycles through these stages multiple times, with each cycle lasting about 90 minutes. REM periods get longer as the night progresses. The first REM period might last only 10 minutes, but by morning, REM periods can extend for 30 minutes or more. The discovery of REM sleep revolutionized sleep research because it provided a window into dreaming that hadn't existed before. Researchers could now observe when someone was likely dreaming based on objective measurements and could wake them at precise moments to collect dream reports. This allowed systematic study of dream content, frequency, and characteristics in ways that simply hadn't been possible before. Research revealed that, while REM sleep is strongly associated with dreaming, dreams can occur in other sleep stages too. NREM dreams tend to be shorter, less vivid, less narrative, and more thought-like. They're often described as thinking rather than experiencing. REM dreams, by contrast, tend to be longer, more visual, more emotional, more bizarre, and more story-like. The content is hallucinatory, filled with perceptions of places, people, and events that feel real in the moment even when they're impossible or absurd. Brain imaging studies using techniques like PET scans and functional MRI have mapped which brain regions are active during REM sleep. Some areas show enhanced activity compared to wakefulness. The pontine tegmentum deep in the brainstem, which seems to help generate REM sleep itself, becomes highly active. The thalamus, which normally gates sensory information to the cortex during wakefulness, is active during REM, but now delivering internally generated signals rather than external sensory data. The amygdala and other limbic structures involved in emotion processing show heightened activity, which may explain why dreams often have such strong emotional content. The visual cortex, particularly areas involved in processing complex visual scenes, lights up during REM sleep. The hippocampus, crucial for memory formation, shows activity patterns suggesting it may be replaying or processing memories. The anterior cingulate cortex, involved in attention and emotional regulation, is active. Meanwhile, other brain regions show decreased activity during REM compared to wakefulness. The dorsolateral prefrontal cortex, involved in executive function, logic, and metacognition, is relatively quiet. This might explain why dreams so often lack the logical coherence and self-reflection that characterize waking thought. We accept impossibilities in dreams without question because the part of the brain that would normally step back and say, "Wait, that doesn't make sense," is not fully online. The patterns of brain activity during REM sleep suggest that dreaming involves a unique state of consciousness where internally generated sensory information, especially visual and emotional content, is processed by many of the same brain regions that handle external perception during wakefulness, but without the reality testing and executive control that normally accompany waking experience. It's as if the brain is running simulations using its perceptual and emotional systems, creating rich experiences from internal models rather than external inputs. This brings us to one of the most intriguing questions about dreams. How does the brain handle time during these internal simulations? In waking life, we perceive time as flowing steadily, one moment following another in a structured sequence. But in dreams, time seems to behave differently. Dream narratives can jump forward and backward. Events that should take hours seem to occur in minutes. Occasionally, something in the external world, like an alarm clock, gets incorporated into a dream in ways that suggest the entire dream narrative might have been constructed in an instant to explain the external stimulus. So how does dream time relate to real time? When you experience what feels like hours in a dream, how long has actually passed? This is where things get really interesting. The question of how time flows in dreams has intrigued humanity for as long as we've been curious about our inner experiences. Ancient texts describe dreams that seem to span years but occurred in a single night. Philosophers have wondered whether dream experiences unfold in real time or whether the mind might construct entire narratives instantaneously. The question remained largely unanswerable until the discovery of REM sleep provided tools to study dreaming scientifically. One of the most famous anecdotes about dream time comes from the mid-19th century, from a French scholar named Alfred Maury. Maury reported a dream in which he had traveled back in time to the French Revolution. In his dream, he witnessed terrible events, was arrested, put on trial, convicted of treason, and sentenced to death by guillotine. He was led to the execution, placed on the apparatus with his head on the lunette, and watched the blade descend toward his neck. At the moment the blade would have struck, he woke with a sharp pain in his neck. When he looked around, he discovered that his canopy bed had collapsed and a piece of the bed frame had fallen and hit him on the neck. Maury theorized that his entire elaborate dream, with its complex narrative spanning revolutionary France, trial, and execution, must have been constructed instantaneously at the moment the bed frame struck his neck. His brain, receiving the pain signal, wove it into a dream narrative that explained the sensation and created the entire backstory in the blink of an eye to give context to the final moment of impact. This idea, that dreams might unfold far faster than real time, or might even occur instantaneously with only the illusion of temporal duration, became influential in early dream research. But was Maury correct? Do dreams really compress time in this way? With the discovery of REM sleep and the ability to wake people during dreams and collect reports, researchers could finally test these ideas empirically. The challenge was finding a way to measure dream duration objectively. Dream reports after awakening are notoriously unreliable for timing because memory for dreams fades quickly and selectively, and there's no guarantee that the remembered dream corresponds accurately to what was actually experienced during sleep. This is where lucid dreaming became crucial. Lucid dreams are dreams in which the dreamer becomes aware that they're dreaming while still asleep. In a lucid dream, you realize your inner dream, and often you can exert some control over the dream content or your actions within it. Importantly, for research purposes, lucid dreamers can perform prearranged actions while dreaming, and some of these actions have observable effects that can be measured from outside. The breakthrough came in the 1970s when researchers realized that eye movements are one of the few motor activities that aren't suppressed during REM sleep. A lucid dreamer can move their eyes in a predetermined pattern like left, right, and this pattern will show up in the electrooculogram recordings monitoring their eye movements. Suddenly, Researchers had a way for dreamers to send signals from inside their dreams to the outside world. A lucid dreamer could signal when they became lucid by making specific eye movements. They could signal when they started a task and when they finished it. This allowed, for the first time, objective measurement of dream time. Stephen LaBerge, a researcher at Stanford University who pioneered much of this work, conducted a pilot study in 1985 with lucid dreamers. He asked participants to count from 1 to 10 in their lucid dreams while signaling the start and end of the counting with predetermined eye movements. The striking result was that the time taken to count from 1 to 10 in a lucid dream was essentially the same as the time taken to count from 1 to 10 while awake. Dream time, at least for this cognitive task, matched real time. Other research teams expanded on this work. Daniel Erlacher and Michael Schredl, researchers in Germany and Switzerland, conducted studies where lucid dreamers performed various tasks in their dreams, while signaling the start and end with eye movements. For counting tasks, dream time continued to match waking time quite closely. But when they asked lucid dreamers to perform motor tasks, something interesting emerged. When participants performed 10 deep knee bends, squats, in their lucid dreams, the task took about 40% longer than it did while awake. Similar results appeared for other motor tasks like walking a certain number of steps or performing a gymnastics routine. Motor activities in dreams took longer than the same activities while awake, but counting and other cognitive tasks didn't show this time extension. Why would motor tasks take longer in dreams? The researchers suggested several possibilities. One is that during sleep, the motor cortex is largely disconnected from the muscles due to the atonia of REM sleep. When you dream of performing a motor action, your brain generates the motor commands, but it doesn't receive the normal sensory feedback from muscles and joints that would occur if you were actually moving. This lack of proprioceptive feedback might make dream movements feel slower or require more neural processing time to simulate. It's possible that, without the rapid feedback loops that guide movement in waking life, the brain has to construct motor actions in dreams more slowly, piece by piece, relying more on prediction than on actual sensory information. Another possibility is that neural processing during REM sleep simply operates at a different speed than during wakefulness. The patterns of neural activity during REM are similar to waking in many ways, but they're not identical. The specific balance of neurotransmitters, the patterns of neuronal firing, the way information flows between brain regions, all of this differs during REM sleep. It's conceivable that these differences result in slower processing speeds for certain types of neural computation. Yet despite these fascinating findings about motor task timing, the overall picture that emerged from lucid dreaming research was surprising to many who had assumed dream time was radically different from waking time. For cognitive activities, for narratives, for experiences that don't involve motor simulation, dream time appears to flow at roughly the same rate as waking time. A dream that subjectively feels like it lasted 5 minutes probably did last about 5 minutes of real time. This contradicts Maury's guillotine dream theory. His elaborate dream of the French Revolution almost certainly didn't occur instantaneously when the bed frame struck him. More likely, he was already dreaming, perhaps already dreaming about the revolution, and the pain from the falling bed frame got incorporated into the existing dream narrative, providing a dramatic ending. We know that external stimuli can be woven into dreams. A ringing phone might become a ringing bell in a dream. A door slamming might become an explosion. The brain, receiving sensory information even during sleep, interprets it within the context of the ongoing dream narrative. Maury's dream was probably already in progress, already unfolding in real time through the stages of arrest and trial, and the pain simply provided a fitting conclusion. But if dream time generally matches real time, why do so many people feel like their dreams compress or expand time? Why does it sometimes feel like you've experienced hours of events in what you know was only a brief sleep? The answer likely lies in how we remember and reconstruct dreams after waking, rather than in the actual temporal structure of the dream experience itself. Memory for dreams is notoriously fragile and selective. Dreams begin to fade from memory within seconds of waking. Unless you actively rehearse a dream or write it down immediately, most of the details vanish. What remains tends to be emotionally salient moments, narrative turning points, striking images, the general storyline. The connective tissue that link these moments together, the mundane transitions and contextual details, fade away fastest. When you remember a dream later, your brain reconstructs a narrative from these fragments. It might feel like your dream covered a lot of ground, jumping from scene to scene, and your waking mind fills in the impression that all these events must have taken a long time to unfold. But the actual experience during the dream may have been more compressed, with less detail, between key moments than your memory suggests. Alternatively, you might remember only a single vivid scene from what was actually a longer dream, creating the impression that the dream was briefer than it really was. There's also the phenomenon of dream time compression through narrative convention. Dreams, like stories, can jump forward in time. You might dream of starting a journey and then suddenly find yourself at your destination without experiencing the travel itself. The dream has skipped over the intervening time, but the narrative structure still implies that time has passed. When you remember such a dream, you might describe it as spanning hours or days, even though the actual experienced moments add up to only minutes. Emotional intensity also affects time perception, both in waking life and in dreams. When you're deeply engaged emotionally, whether through fear, excitement, joy, or sorrow, time often seems to slow down. A frightening experience can feel like it's unfolding in slow motion, even though later you realize it lasted only seconds. Dreams are often intensely emotional, and this emotional intensity might distort the subjective sense of how much time has passed, making emotionally charged dream sequences feel longer than they objectively were. Another factor is that dreams often lack the typical markers we use to judge time passage in waking life. In daily life, we constantly refer to clocks, notice the sun's position, feel hunger or fatigue, use these cues to calibrate our sense of elapsed time. Dreams rarely include reliable temporal markers. You might look at a clock in a dream and see a time, but if you look again, it might show a completely different time without any sense that time has passed. The absence of consistent temporal cues makes it harder to judge how long a dream experience lasted. Then there's the issue of multiple dream periods in a single night's sleep. As mentioned earlier, we cycle through REM sleep multiple times each night, with REM periods getting longer toward morning. You might have 5 or 6 separate REM periods, each with its own dreams. But when you wake up, you might remember fragments from several different dreams and unconsciously stitch them together into what feels like a single, continuous narrative. This can create the impression of a very long, elaborate dream, when what actually occurred was several shorter dreams separated by other sleep stages and intervening time that you don't remember at all. All of these factors, memory selectivity, narrative reconstruction, emotional intensity, lack of temporal cues, and the consolidation of multiple dreams can distort our retrospective sense of dream duration. The actual experience during the dream likely flows at close to real-time speed, at least for cognitive and narrative content, but our memory and interpretation of that experience after waking can make it seem like time in dreams operates according to completely different rules. This raises an interesting parallel to physics. In relativity, time is observer-dependent. How fast time flows depends on your reference frame, your velocity, your position in a gravitational field. Similarly, in dreams, the perception of time is consciousness-dependent. The actual neural processes underlying the dream might unfold in measurable real time, but the subjective experience of that time, and especially the memory and interpretation of that experience after the fact, can vary dramatically depending on cognitive and emotional factors. Just as there's no single objective time in Einstein's universe, there's no single objective time in the landscape of consciousness. Both are relative to perspective. Let's explore lucid dreaming in more depth, because it provides our most powerful tool for studying dream time scientifically. Lucid dreaming has been known about for centuries. Tibetan Buddhist practices include dream yoga, techniques for maintaining awareness during dreams. Western philosophers and writers have described lucid dreams. But it wasn't until the late 20th century that lucid dreaming became a subject of serious scientific research. The key breakthrough, as mentioned earlier, was the realization that lucid dreamers could voluntarily control their eye movements during REM sleep, and that these movements could be detected by researchers monitoring the sleeper's EEG and eye movement patterns. This provided a communication channel between the dream world and the waking world. For the first time, someone could say, "I'm about to perform an experiment in my dream," signal with their eyes that the experiment was starting, perform the task in the dream, and signal again when it was complete. The time between signals could be measured objectively. Stephen LaBerge was instrumental in developing these techniques. He trained himself and other participants to become lucid in their dreams reliably. His studies in the 1980s provided the first solid evidence that dream time runs roughly parallel to real time. In one of his classic experiments, lucid dreamers were instructed to make specific eye movement signals when they became lucid, then to estimate intervals of 10 seconds multiple times while in the dream, signaling with eye movements between each interval. The time taken to estimate 10 seconds in a lucid dream averaged about 13 seconds of real time, close enough to suggest that dreamers' internal time sense during lucid dreams was fairly accurate. But the most intriguing findings came from studies comparing different types of tasks. Erlacher and Schredel's work, building on LaBerge's foundation, showed that while counting and other cognitive tasks took roughly the same time in dreams as in waking, motor tasks consistently took longer in dreams. In their studies, lucid dreamers performed tasks like squatting, walking, or executing gymnastic movements, signaling the start and end of each task with predetermined eye movement patterns. The results were consistent. Motor tasks in lucid dreams took between 20 and 50% longer than the same tasks performed while awake, with an average around 40% slower. This wasn't due to participants simply being imprecise in their dream timing. When they performed counting tasks or singing tasks, activities that don't involve motor simulation, the timing matched waking performance much more closely. There was something specifically about simulating physical movement in dreams that made the experience unfold more slowly than waking movement. Imagine you're lucid in a dream and you decide to do 10 squats. You start bending your knees, lowering yourself, standing back up over and over. In the dream, the experience might feel normal, like you're moving at your usual pace. But if researchers are measuring the actual clock time from when you signal the start to when you signal completion, they find it takes longer than 10 squats would take if you got out of bed and did them for real. Your dream body moves in slow motion relative to your waking body, even though from inside the dream, the motion might feel normal. Why does this happen? One theory involves the role of sensory feedback in motor control. When you perform a movement while awake, your brain sends motor commands to your muscles, but it also continuously receives feedback. Proprioceptors in your muscles and joints tell your brain where your limbs are and how fast they're moving. Visual information confirms what you see yourself doing. Vestibular information from your inner ear tracks your balance and orientation. This rich stream of sensory feedback allows your brain to make constant adjustments, keeping your movements smooth and coordinated. In a dream, none of this sensory feedback is present. Your muscles are paralyzed by REM atonia. You're not actually moving. When you dream of moving, your motor cortex generates the commands for movement, but the usual feedback loops are absent. Your brain has to simulate the entire experience internally, predicting what the movement should feel like based on stored memories and internal models. This prediction-based simulation might take longer than the real-time perception-action feedback loop that operates during waking movement. Another factor could be the speed of neural processing in different brain states. During waking movement, many neural processes happen in parallel. Multiple brain regions work simultaneously to plan, execute, and monitor movement. During REM sleep, the pattern of brain activation is different. Some regions are more active than during wakefulness, others less so. The communication between regions may follow different pathways or timing patterns. It's possible that the neural processes required to simulate motor experience during REM sleep simply take longer to complete than the processes that control actual waking movement. There's also a possibility that attention plays a role. Motor simulation in dreams might require more conscious attention than motor execution while awake. Once you've learned to walk or squat, much of the control becomes automatic during waking life. Your conscious mind can focus on other things while motor subroutines handle the details. In a dream, without sensory feedback to guide these subroutines, more conscious attention might be needed to construct the experience of movement, and this additional cognitive load might slow the process down. Whatever the mechanism, the lucid dreaming research reveals that dream time is not uniform. It's not simply that everything in dreams runs at the same speed, whether matched to real time or compressed or expanded by some constant factor. Instead, different types of mental content unfold at different rates. Cognitive tasks, narrative thinking, conversations, all seem to flow at roughly real-time speed. But motor simulation runs slower, taking perhaps 40% longer than waking motor activity. This has interesting implications. It suggests that the dreaming brain handles different types of information processing at different speeds, that the subjective flow of time in dreams is not monolithic, but rather varies depending on what kind of mental content is being generated. It also suggests that the subjective sense of time within a dream, what it feels like to the dreamer as they experience the dream, might not always match the objective duration of the dream as measured by external observers watching brain activity and eye movements. For someone interested in both physics and neuroscience, there's a tantalizing parallel here. In Einstein's relativity, different observers can measure different time intervals for the same events depending on their motion and position in a gravitational field. Time is not absolute but relative to the observer. In dreams, different types of mental processes appear to unfold at different rates, and the subjective experience of time can differ from the objective measurement of neural activity duration. Time in consciousness, like time in physics, resists simple absolute characterization. It depends on the frame of reference, on what's being measured, on the perspective from which the measurement is made. To understand why time behaves the way it does in dreams, we need to look more closely at what's happening in the brain during REM sleep. Modern neuroscience has given us powerful tools to peer into the sleeping brain, and what we've learned is that REM sleep involves a complex and specific pattern of brain activity that differs in important ways from both waking consciousness and other sleep stages. Let's start with the brainstem. Deep structures in the pons, part of the brainstem, play a crucial role in generating REM sleep. Neurons in the pontine tegmentum begin firing in characteristic patterns that trigger the constellation of features we associate with REM. The rapid eye movements, the muscle atonia, the activation of cortical areas. These pontine neurons use acetylcholine as their neurotransmitter, and cholinergic activity is particularly high during REM sleep. This is important because acetylcholine is involved in attention and memory formation. The activation from the brainstem spreads upward through the thalamus to the cortex. The thalamus acts as a relay station, and during REM sleep it's highly active, but unlike during waking, when it's primarily relaying sensory information from the outside world, during REM it's relaying internally generated signals. The thalamus is, in a sense, feeding the cortex with pseudosensory information, patterns of activity that the cortex interprets as perceptions even though they don't originate from any external stimulus. The cortical areas that receive this activation during REM include primary and secondary visual cortex. This is why dreams are predominantly visual. The same areas that process visual information during waking consciousness are active during REM, but now they're responding to internally generated activity patterns rather than signals from the eyes. The brain is quite literally seeing things that aren't there, hallucinating rich visual experiences. The hippocampus, crucial for forming new memories and spatial navigation, shows characteristic theta rhythm activity during REM sleep. The hippocampus also shows replay of activity patterns, suggesting it might be processing and consolidating memories during dreams. Some theories propose that one function of REM sleep and dreaming is memory consolidation, that the brain is reviewing and integrating experiences from waking life, strengthening some memories and weakening others based on their significance. The amygdala and other limbic structures involved in emotional processing are highly active during REM sleep, often more active than during waking. This might explain why dreams are so frequently emotional, why they can evoke strong feelings of fear, anxiety, joy, or desire, the emotional content of dreams isn't a side effect. It's a central feature driven by the enhanced activity of emotional processing regions. Meanwhile, some areas show decreased activity during REM compared to waking. The dorsolateral prefrontal cortex, involved in executive function, working memory, logical reasoning, and metacognition, is relatively quiet. Activity in this region during waking consciousness is associated with our ability to think about our thinking, to evaluate whether our thoughts make sense, to maintain focus on goals and tasks. The reduced activity in this area during REM might explain some classic features of dreams: the lack of logical coherence, the acceptance of impossibilities without question, the difficulty maintaining sustained focus on any single topic, the poor memory for the dream upon waking. This pattern of activation, high activity in sensory, emotional, and memory, related areas combined with low activity in executive control areas, creates the distinctive phenomenology of dreaming. We experience rich perceptual and emotional content, but without the reality checking and logical evaluation that would normally accompany such experiences. We're immersed in the dream, experiencing it as real, unable to step back and recognize it as the internally generated simulation it actually is unless we achieve lucidity. But what about time perception specifically? How does the brain construct the sense of time flow during dreams? Time perception is not handled by a single brain region. It's an emergent property arising from the interaction of multiple neural systems. Different aspects of time perception, from millisecond timing needed for motor control to the sense of hours passing during an event, involve different neural mechanisms. One key area for time perception is the cerebellum, traditionally known for motor coordination, but increasingly recognized as important for timing. The cerebellum is active during REM sleep, though patterns of cerebellar activity differ from waking. The basal ganglia, another motor control area also involved in timing, shows modified activity during REM. These altered patterns in motor timing circuits might contribute to the slower time course of simulated movements in dreams. The prefrontal cortex, particularly areas involved in working memory, plays a role in estimating longer durations and in consciously attending to time passage. The reduced prefrontal activity during REM might affect explicit time judgments, making it harder to accurately estimate how much time has passed or to maintain attention on temporal aspects of experience. The hippocampus and surrounding medial temporal lobe structures are crucial for episodic memory, our memory for events in their temporal context. When you remember an event from your past, you don't just remember what happened. You remember when it happened relative to other events, and you have a sense of how long it lasted. The hippocampus helps construct this temporal framework for memories. During REM sleep, the hippocampus is active but operating in a different mode than during waking encoding of new memories. It might be replaying stored memories, recombining elements from different experiences, creating novel narratives from familiar components. This recombination process might explain why dream narratives often feel temporal, like they unfold over time, even though the actual construction might be happening through a process more like memory retrieval than real-time experience. When you remember a past event during waking, you can access the memory quickly, but the memory itself has temporal structure, a beginning, middle, and end, that unfold in your mind's eye as you recall it. Dreams might work similarly, accessing and recombining memory fragments that have their own temporal structure, creating the experience of events unfolding even though the neural process of constructing that experience might not take as long as the subjectively experienced duration. There's also the question of attention and its role in time perception. Studies in waking consciousness have shown that time perception is highly dependent on attention. When you're focused on time itself, watching a clock or waiting for something, time feels like it passes slowly. When you're absorbed in an activity and not attending to time, it seems to fly by. In dreams, attention is fluid and unstable. Your focus shifts rapidly from one dream element to another. You rarely attend to time itself as a feature of the dream. This lack of attention to temporal aspects might contribute to the malleability of time sense in dreams. The neurochemical environment during REM sleep also differs from waking. As mentioned, acetylcholine levels are high. Serotonin and norepinephrine, which are present during waking consciousness, are largely absent during REM sleep. These neurotransmitters have complex effects on cognition and time perception. Their absence during REM might alter the speed or efficiency of certain neural processes, contributing to differences in how time is experienced or how quickly different types of mental content can be generated. One fascinating finding from recent neuroscience research is that the brain doesn't simply record experience like a video camera running at constant speed. Instead, it samples information in rhythmic bursts. Neural oscillations at different frequencies, alpha waves, theta waves, gamma waves, reflect cycles of enhanced and reduced neural excitability. Perception and cognition might be fundamentally rhythmic, happening in discrete moments strung together rather than as a truly continuous stream. During waking consciousness, these rhythms are coordinated across brain regions in characteristic ways. During REM sleep, the rhythmic structure is different. Theta oscillations are prominent, especially in the hippocampus. Gamma oscillations, associated with conscious awareness and binding of features into coherent perceptions, occur but with different patterns than during waking. These altered rhythmic structures during REM might change the fundamental temporal grain of experience, how finely time is sampled, how quickly successive moments of experience can be generated. All of this neural activity, the activation patterns, the neurochemical environment, the oscillatory rhythms, the interplay between memory, emotion, and perception creates the unique phenomenology of dreaming. And embedded within this phenomenology is a sense of time that both resembles and differs from waking time perception. The brain constructs time in dreams using many of the same neural mechanisms it uses during waking, but operating under different conditions, with different patterns of activity, creating an experience of time that sometimes matches, sometimes diverges from, the objective flow of neural process duration measured by external observers. Let's step back from the specific mechanics of dreaming and think more broadly about consciousness and time perception. The experience of time is one of the most fundamental and mysterious aspects of consciousness. We all experience time flowing, carrying us from past through present into future. Moments seem to succeed one another in a stream. And yet, neuroscience and psychology reveal that this simple picture is profoundly misleading. Consider what's called the specious present, a concept articulated by psychologist William James in the late 19th century. When you experience the present moment, you don't experience just a single instant, an infinitesimal slice of time with no duration. Instead, you experience a span of time, a psychological present that has duration, typically estimated at somewhere between 2 and 3 seconds. This is the window of time that feels like now. Think about listening to a melody. You don't hear each note as an isolated present event disconnected from what came before and after. You hear a phrase, several notes strung together into a musical gesture that occupies time. The phrase is present to your consciousness as a unified experience, even though objectively the notes occur in succession. Your psychological present holds multiple moments together into a coherent perceptual unit. This means that what you experience as the present moment is actually already a construction, a synthesis that your brain has created by integrating information across a short span of time. The present you experience is not the objective physical present, that infinitesimal boundary between past and future. It's a subjective, extended present built by your nervous system. Time perception is also highly context-dependent. We've all experienced moments where time seems to slow down, situations of intense fear or focus where everything happens in slow motion, and you have what feels like extra time to react. We've also all experienced the opposite, absorption in an enjoyable activity where hours pass in what feels like minutes. These aren't just subjective impressions. They reflect genuine differences in how much information your brain processes and how it calibrates its sense of elapsed time. When you're in a frightening or intensely novel situation, your brain goes into high gear. Attention sharpens. Memories are encoded with more detail. Later, when you recall the experience, you retrieve unusually rich memory with many details. Your brain interprets this richness as meaning the experience must have lasted longer than it actually did. In reality, your perception wasn't slower in the moment, but your memory makes it seem like it was because of how much you remember. Studies have shown that people don't actually perceive events more slowly during frightening experiences, but they remember them as having lasted longer. Conversely, when you're engaged in a familiar, enjoyable activity, you might not encode as many memories because nothing particularly novel is happening. Later, when you try to recall the time period, you retrieve fewer memories, and your brain interprets this paucity as meaning less time must have passed. Time flies when you're having fun, not because it actually moves faster during enjoyable experiences, but because you encode fewer memories when you're not attending to time's passage, and this leads to retrospective time compression. Emotional state profoundly affects time perception. When you're bored or waiting for something, time crawls. When you're anxious, time can seem to simultaneously drag because you're focused on waiting and race forward because you're anticipating something. Depression often involves a sense of time moving slowly, the present stretching out, the future seeming distant and unreachable. Mania involves a sense of time speeding up, thoughts racing, too much happening too quickly. Age also affects time perception. Many people report that time seems to speed up as they get older. There are several proposed explanations for this. One is that novel experiences, which are more common in childhood when everything is new, are encoded more richly, making time feel slower in retrospect. As you age and experiences become more familiar, you encode fewer distinctive memories, and time seems to pass faster. Another explanation involves proportionality. A year is a much larger fraction of your experienced life when you're 5 than when you're 50, so subjectively, it might feel longer. A third explanation focuses on attention. Children might pay more attention to time itself, constantly monitoring how much longer until some anticipated event, whereas adults often don't attend to time's passage in the same way. All of this shows that time perception is not a simple readout of some objective clock in the brain. It's a construction built from multiple sources of information modulated by attention, emotion, and memory, varying across contexts and states of consciousness. What we experience as time flowing is an interpretation, a model that our brain creates to organize experience and guide action. In waking consciousness, this model is usually fairly stable and consistent. Clocks and social coordination keep everyone's time sense roughly aligned. But in dreams, many of the anchors that normally stabilize time perception are absent. There are no clocks to check, no external events unfolding at measurable rates, no social expectations about time, no consequences for misestimating duration. The brain is free to construct time more flexibly, perhaps explaining why dream time can feel so variable, even though the underlying neural processes appear to run at roughly real-time speeds. This raises profound questions. If time perception is constructed by the brain rather than directly perceived, in what sense does time have an objective reality? Einstein taught us that there's no universal time in physics, that temporal intervals depend on reference frames. Now, neuroscience suggests there's no universal time in consciousness either, that the experience of time is constructed differently across contexts, states, and individuals. Is time a feature of the universe, or is it primarily a feature of how minds organize information? Physics tells us that space-time has a real geometric structure. Events have temporal relations. Light cones define causal structure. These aren't arbitrary or illusory, but the division of space-time into past, present, and future, the flow of time from one moment to the next, these might be features of consciousness rather than features of space-time itself. The equations of physics are time-symmetric. They work equally well running forward or backward. The psychological arrow of time, the sense that we're moving from past toward future, might be something minds impose on the universe rather than something the universe inherently possesses. Dreams, where time can feel so strange, might give us clues about the nature of consciousness and its relationship to time. In dreams, we're still conscious. We still experience succession, moments following one another, but the construction is more obvious, the seams show more clearly. The disconnection between the subjective experience of time in the dream and the measurable neural activity producing that experience highlights how much of our temporal experience is interpretation rather than direct perception. In both physics and consciousness, time is observer-dependent. But the observers in physics are still external, measuring and comparing reference frames. The observer in consciousness is internal, generating experience from the inside. Both perspectives suggest that time is not the simple, absolute, universal flow we naively imagine. It's something more subtle, more relational, more dependent on context and perspective. Whether we're talking about twin paradoxes or lucid dream experiments, time reveals itself to be deeply mysterious. We've journeyed through two landscapes where time behaves strangely. In the cosmic realm of relativity, time dilates near massive objects and at high velocities. In the mental realm of dreams, time perception becomes untethered from external clocks, subjectively compressing or expanding. These seem like utterly different phenomena, one physical and objective, one psychological and subjective. But are they really as separate as they first appear? Let's explore the connections. At first glance, relativistic time dilation and dream time distortion seem to have nothing in common. Relativistic effects are real physical phenomena measured by clocks. They're predictable, quantifiable, built into the structure of space-time itself. Dream-time distortions are features of subjective experience, inconsistent, difficult to measure, arising from the idiosyncrasies of neural processing during sleep. One is physics, the other psychology. One is objective, the other subjective. But look deeper and resonances emerge. Both challenge the common sense notion of absolute, universal time. Both show that time is not the simple fixed framework we imagine. Both reveal time to be dependent on context and perspective. In relativity, time's flow depends on your motion and your position in a gravitational field. In consciousness, time's flow depends on your brain state and what cognitive processes are active. Here's a thought experiment. Imagine you could directly compare the experiences of two observers, one near a black hole experiencing extreme gravitational time dilation, another far away in flat space-time. From the outside observer's perspective, the near-horizon observer's time has almost stopped. But from the near-horizon observer's perspective, their own time flows normally. They don't experience any slowing. If that observer were conscious and thinking, would their thoughts seem slower to them? Or would they think at what seems to them a normal rate, even though from the outside observer's perspective, it's taking them years to complete a thought? Physics doesn't tell us because it deals with measurable quantities like clock rates, not with subjective experiences. But it's a fascinating question. If a brain existed in a region of extreme time dilation, and neural processes took what an outside observer measured as hours to complete what the brain experienced as milliseconds, which perspective would be correct? Or is correctness even the right concept when dealing with observer-dependent realities? Now consider dreams. When motor simulation in a lucid dream takes 40% longer than the same motor task while awake, where does that extra time go? From the perspective of researchers measuring eye movement signals, the dream task takes more clock seconds. But from the dreamer's perspective, the task might feel like it's taking the normal amount of time. The dreamer isn't consciously aware that their dream movements are slow, they're just performing the task. There's a disconnect between the objective time measured externally and the subjective time experienced internally. This parallels relativity in an interesting way. In both cases, there's no single correct answer to how much time has elapsed. It depends on your frame of reference. For external observers measuring brain activity, the dream task took X seconds. For the dreamer experiencing the task from inside, it might have felt like Y seconds. Both are valid descriptions of the same event from different perspectives. Of course, the analogy isn't perfect. Relativistic time dilation is reciprocal and consistent. If observer A sees observer B's time running slowly, then B sees A's time running slowly as well, in a symmetrical way dictated by the equations of relativity. Dream time distortions don't show this kind of symmetry or mathematical consistency. They're messier, more variable, less predictable. But the fundamental insight is similar. Time is not absolute. It depends on context and perspective. There's another parallel. Both physical time dilation and psychological time perception involve real changes, not just illusions or misperceptions. When a GPS satellite's clock runs faster due to being in a weaker gravitational field, that's not an artifact of measurement or a trick of perspective. The satellite's clock genuinely accumulates more seconds. Time itself is flowing faster there. Similarly, when neural processes during dream motor simulation take longer than waking motor execution, that's not just a subjective impression. The brain is actually taking more time to generate the simulated experience. The neural processes themselves are slower, even if the dreamer might not consciously perceive that slowness. In both cases, time is doing something real and measurable. It's not just that our perception of time is changing. The actual flow of time, whether measured by the evolution of physical systems like orbiting satellites or the evolution of neural systems like dreaming brains, genuinely varies depending on context. Let's think about the role of observers in both domains. In relativity, an observer is any entity that can make measurements, that has a reference frame, that experiences a timeline through space-time. The observer's motion and position determine how they slice space-time into space and time, what events they consider simultaneous, how they measure durations and distances. Different observers with different motions slice space-time differently, leading to different measurements of time and space. In consciousness research, the observer is the experiencing subject, the mind that has experiences. The observer's brain state, their emotional condition, what they're attending to, whether they're awake or dreaming, all these factors determine how time is experienced. Different mental states lead to different experiences of temporal flow, duration, and succession. In both physics and psychology, the observer is not separate from the reality they observe. The observer is embedded in and part of the phenomenon. This is clearest in quantum mechanics, where measurement itself affects what is measured, but it's true in relativity as well. There is no view from nowhere, no perspective outside all reference frames. Every observation is made from within some reference frame, and the reference frame shapes what is observed. The same is true for consciousness. There is no experience of time that is not someone's experience, some mind's construction. We can't step outside our own consciousness to see what time really is independent of any observer. All we can access is how time appears to various observers, including ourselves in various states. The subjective experience of time is the only kind of temporal experience there is from the inside perspective. This suggests a deep truth. Time, both in physics and in consciousness, is fundamentally relational and perspectival. It's not an absolute backdrop existing independently of observers. It's something that emerges from the relationships between events and observers, from the structure of space-time and from the architecture of minds. Einstein showed us this for physical time. Neuroscience suggests something similar for experiential time. Does this mean time is illusory? That's a question philosophers have debated endlessly. If time is observer-dependent, does that make it less real? Or is observer dependence itself a feature of reality rather than evidence of illusion? After all, temperature is observer-dependent in a sense. Hot and cold are meaningful only relative to an observer with a particular thermal state. But temperature corresponds to real physical properties, the kinetic energy of particles. It's not an illusion just because it's relational. Similarly, time might be relational and observer-dependent while still corresponding to real features of the universe. In physics, time is part of the geometry of space-time, and that geometry has observer-independent features even though different observers slice and measure it differently. In consciousness, time perception might be constructed and variable, but it's constructed from real neural processes occurring at real rates and reflects genuine features of how information flows through the brain. Perhaps the right way to think about it is that time has both objective and subjective aspects. Objectively, there's the structure of space-time, the causal relationships between events, the rates at which physical and neural processes unfold. Subjectively, there's the experience of time flowing, moments succeeding one another, duration extending. These two aspects are related but not identical. The subjective arises from the objective, but the relationship is complex, mediated by the observer's state and context. Dreams highlight this beautifully. The objective neural processes of REM sleep unfold at measurable rates. Researchers can time them with clocks. But the subjective experience of the dream, what it feels like from the inside, may not align perfectly with those objective measurements. The felt duration, the sense of how much time is passing, the experience of succession and simultaneity, these are constructed by the dreaming mind based on the neural activity but not identical to it. Relativity teaches us that there's no privileged reference frame, no absolute perspective from which time has a uniquely correct value. Every observer's measurements are equally valid within their own reference frame. Similarly, perhaps there's no privileged perspective from which the duration of a dream has a uniquely correct value. The external researcher measuring seconds of REM sleep and the internal dreamer experiencing the narrative both capture real aspects of the phenomenon, just from different perspectives. This leads to a fascinating possibility. Perhaps the study of consciousness and the study of space-time are both telling us something fundamental about the nature of time itself. Time is not a thing that exists independently of everything else. It's a relationship, a structure that emerges from the way events and processes and observers are organized. In physics, that structure is geometric, built into the curvature of space-time. In consciousness, that structure is experiential, built from the flow of information through neural networks. But maybe these aren't separate structures. Maybe they're different aspects of the same underlying reality. After all, consciousness arises from physical processes in the brain, and those physical processes are embedded in space-time. When you experience time flowing, that experience is itself a physical process unfolding in time. There's a loop, a strange recursive structure where time generates experiences of time, where physical temporal evolution creates conscious temporal awareness. Understanding this loop, this relationship between physical time and experiential time, might be one of the deepest challenges in both physics and neuroscience. How does the objective third-person time of physics give rise to the subjective first-person time of experience? Why does time flow for consciousness when the equations of physics don't distinguish past from future? How can time be both the geometrical structure Einstein described and the felt flow William James described? These questions remain open, but exploring them through the lens of relativistic physics and dream research, through GPS satellites and lucid dreamers, through black holes and REM sleep, reveals just how rich and mysterious time truly is. It's not the simple, obvious thing we take it to be in everyday life. It's stranger, deeper, more intimately connected to consciousness and to the structure of reality than we typically realize. The strange behavior of time in both relativistic physics and dreaming consciousness raises profound philosophical questions. These aren't just abstract puzzles. They touch on fundamental issues about the nature of reality, consciousness, and our place in the universe. Let's explore some of these deeper implications. First, consider what dreams tell us about the nature of consciousness itself. When you dream, you have experiences that feel real. You see places, hear sounds, feel emotions. You interact with dream characters and navigate dream environments. All of this is happening, but it's happening entirely inside your skull. Your sensory systems are disconnected from the external world. You're experiencing a fully immersive virtual reality generated by your own brain with no external input. This reveals something remarkable about consciousness. The vividness, the sense of presence, the feeling that you're perceiving a real world out there, all of that can be generated entirely internally. The brain doesn't need actual sensory input to create perceptual experiences. It can hallucinate an entire world and make that world feel completely real. This suggests that even during waking consciousness, what we experience as perceiving the external world might be better understood as the brain's best guess about what's out there, a controlled hallucination constrained by sensory input but still fundamentally constructed rather than directly accessed. If the brain can create the experience of time flowing, of moments succeeding one another, of events having duration, all within a dream where no real time-dependent processes are occurring in the external world, then perhaps the experience of time is also something the brain constructs rather than something it directly perceives. Time might be a feature of how consciousness organizes information rather than a feature we passively read off from the world. This leads to deep questions about the relationship between experience and reality. In philosophy of mind, this is sometimes framed as the question of qualia, the subjective, qualitative aspects of experience. What is it like to see red? What is it like to feel pain? These subjective experiences seem to have properties that can't be fully captured by objective descriptions of brain activity. You can describe the neural processes involved in pain perception in complete detail, but that description doesn't seem to convey what pain actually feels like. The experience of time might be a kind of qual. What it feels like for time to pass, the qualitative sense of duration and flow, might be something that emerges from neural processes but can't be fully reduced to those processes. This would explain the disconnect between objective measurements of dream duration and subjective experiences of how long dreams feel. The objective measurements capture one aspect of reality, the actual unfolding of neural processes in physical time. The subjective experiences capture another aspect, the qualitative character of what those processes feel like from the inside. This dualistic picture, objective physical processes and subjective experiences as two distinct aspects of reality, has been controversial in philosophy for centuries. Some philosophers embrace it, arguing that consciousness involves something beyond physical processes. Others reject it, insisting that consciousness must be entirely explicable in physical terms, even if we don't yet understand how. The nature of time in dreams doesn't settle this debate, but it does illuminate what's at stake. Now let's connect this to relativity. Einstein's theories showed that time is relative to reference frames, that there's no absolute simultaneous presence spanning the universe, that temporal order can differ for different observers. This challenges some traditional philosophical assumptions. Many philosophers assumed that the present moment was ontologically special, that what exists right now is real, while past and future are somehow less real or unreal. But if there's no unique present, if different observers disagree about what events are happening now, then present moment centrism becomes hard to maintain. One response is eternalism or block universe theory. According to this view, all moments of time, past, present, and future, exist equally. The universe is a four-dimensional block of space-time, and all events are equally real, located at different space-time coordinates. What we call the present is just our current location in this block, and our subjective sense of time flowing is like the experience of driving down a highway. The landscape doesn't cease to exist behind us or begin to exist in front of us. It's all there, and we're moving through it. Except we're not really moving through time in this picture. All our moments exist timelessly in the block. The sense of motion, of time flowing, is a feature of consciousness, of how we experience our world line through space-time, not a feature of space-time itself. This view aligns with the mathematics of relativity, but it conflicts with our subjective experience. It feels like time flows, like the future is open and the past is fixed, like the present is uniquely real. Dreams don't resolve this tension, but they do show that our subjective sense of time can be manipulated and constructed by neural processes without external temporal flow. Maybe the flowing time of experience is indeed something minds generate rather than something they perceive in the world. Alternatively, some philosophers propose presentism, the view that only the present moment exists, but modified to account for relativity's lessons. Perhaps each observer has their own present, their own slice of existence, and these presents differ for observers in different reference frames. This preserves the intuition that presence is special while accommodating relativity's relativity. A third option is growing block theory, the idea that the past and present exist, but the future doesn't yet. The block of existence grows as new moments come into being. This tries to preserve the asymmetry between past and future, The sense that what has happened is fixed, while what will happen is open, while still accommodating multiple reference frames. Different observers might disagree about how far the block has grown, what counts as already existing versus not yet existing. None of these philosophical positions can be definitively proven or disproven by physics or neuroscience alone. They're interpretations, frameworks for making sense of the data. But the data from relativity and from dream research constrain what's plausible. Any philosophical account of time has to explain why time behaves as it does both in space-time and in consciousness. It has to explain time dilation and dream time, the objective and the subjective, the measurable and the felt. Dreams also raise questions about the self and personal identity. When you dream, you often experience yourself as a character in the dream, seeing through their eyes, feeling their emotions. But sometimes that dream character isn't you. Sometimes you're someone else in the dream, or you're watching yourself from outside, or your identity shifts fluidly. The sense of being a continuous self across time, which seems so solid during waking life, becomes flexible in dreams. This connects to philosophical questions about personal identity. What makes you the same person over time? Is it continuity of consciousness? But consciousness gets interrupted every night when you sleep. Is it continuity of memory? But memories are fallible, reconstructive, and many memories fade or change. Is it continuity of the body? But your body's cells are constantly being replaced. Is it continuity of personality and values? But people change, sometimes dramatically, over a lifetime. Dreams show that the experience of being a self, of having a perspective, of being located in time at a particular moment with a particular past and future is constructed by the brain. It can be modified, fragmented, reconfigured. This doesn't necessarily mean the self is an illusion, but it does suggest that it's not the simple, atomic, unchanging entity we sometimes assume it to be. If time and self are both constructed by consciousness, both flexible and context-dependent, then our intuitive picture of reality, a world of enduring objects persisting through absolute time, experienced by stable selves, might be fundamentally mistaken. Reality might be better understood as a web of relationships, processes, and perspectives, with no absolute privileged viewpoint, no unchanging foundation underlying the flux. This is a humbling conclusion. It suggests that our everyday experience, as compelling and vivid as it is, might be deeply misleading about the fundamental nature of things. But it's also exhilarating. It means there's more to reality than what we directly perceive. There are depths and structures and strange connections that we can only discover by looking beyond the surface, by doing physics and neuroscience, by thinking carefully about what our equations and experiments are telling us. The relationship between space-time and consciousness remains one of the great unsolved problems in science and philosophy. We know consciousness arises from physical processes in brains, and we know brains exist in space-time. But how exactly do the dynamics of matter and energy give rise to subjective experience? How does objective, third-person, physical time relate to subjective, first-person, experiential time? These questions remain open, and the answers might require conceptual revolutions as profound as the ones Einstein initiated. We've traveled far together through this exploration of time in its many guises. We've seen how Einstein shattered the illusion of absolute time, showing us that time dilates near massive objects and at high velocities, that simultaneity is relative, that space-time is a unified four-dimensional structure warped by matter and energy. We've seen how black holes take these effects to extremes, creating regions where time, from an outside perspective, seems to stop at the event horizon. We've turned inward to explore the sleeping brain and the phenomenon of dreaming, discovering that REM sleep creates a unique state of consciousness where the brain generates rich hallucinatory experiences disconnected from external sensory input. We've examined research on dream time, learning that while cognitive tasks in lucid dreams seem to unfold at roughly real-time speed, motor simulation runs significantly slower, suggesting that different types of neural processing during REM sleep operate at different rates. We've delved into the neuroscience underlying dreams, exploring the patterns of brain activation during REM sleep, the roles of different regions and neurotransmitters, the oscillatory rhythms that structure neural activity. We've thought about how the brain constructs the experience of time, both in waking consciousness and in dreams, how time perception depends on attention, emotion, memory, and context. We've drawn connections between these two domains, noting that both physical time in relativity and experiential time in consciousness are observer-dependent, context-sensitive, and fundamentally different from the simple, absolute, universal time of everyday intuition. We've explored philosophical implications, questioning the nature of reality, consciousness, and self in light of what physics and neuroscience reveal about time's flexibility. What emerges from all this is a picture of time as something far stranger and more subtle than most of us realize in our daily lives. Time is not a river flowing uniformly throughout the universe. It's not a simple one-dimensional parameter ticking away in the background. It's a complex, multifaceted phenomenon that depends on reference frames and brain states, on gravity and attention, on velocity and neural architecture. In physics, time is part of the geometric structure of spacetime, curved and warped by mass and energy, flowing at different rates for observers in different contexts. In consciousness, time is an experiential construct generated by neural processes to organize information and guide action, variable across mental states and contexts. These two aspects of time, the physical and the experiential, are related but not identical. Understanding their relationship remains one of the deepest challenges in science. Dreams, in particular, offer us a unique window into the constructed nature of temporal experience. When you dream, your brain creates an entire world, complete with the sense of time flowing, events unfolding, duration extending. All of this is generated internally without external time-dependent inputs. This reveals that the experience of time is something minds can create, not something they passively perceive. Even in waking life, our temporal experience might be more of a simulation than a direct readout of physical time. Both relativity and dream research teach us humility about our intuitions. What seems obvious and undeniable, that time flows uniformly, that all observers share the same present moment, that duration is an objective property of events, turns out to be wrong. Reality is stranger than our everyday experience suggests. Time is relative, malleable, observer-dependent. This doesn't make time illusory or unimportant. If anything, it makes it more interesting, more worthy of study and wonder. As you go about your life, as you experience moments flowing from past into future, as you sleep and dream each night, you're participating in this cosmic mystery. Every tick of a clock, every remembered moment, every anticipated future event involves time in all its complexity. You're embedded in spacetime's four-dimensional geometry, moving through it at nearly the speed of light along your world line. You're also a conscious being constructing temporal experience from neural activity, creating the sense of now, of duration, of flow. These two aspects of your relationship to time, the physical and the experiential, come together in you. You are matter and mind, space-time and consciousness, observer and observed. Understanding time means understanding this unity, this strange loop where physical processes give rise to conscious experiences of time and conscious beings study and measure physical time. We're nowhere near a complete understanding. The relationship between space-time and consciousness remains deeply mysterious. How does matter arranged in the right way, neurons firing in particular patterns, give rise to the subjective experience of time flowing? How do objective time intervals measured by clocks relate to subjective durations experienced by minds? These questions remain at the frontier of science and philosophy, but what we've learned so far is already astonishing. Time is not what we thought it was. It's richer, stranger, more dependent on context and perspective than everyday experience suggests. Whether we're contemplating astronauts aging more slowly in orbit, imagining clocks near black holes, or examining our own dreams where hours might feel like minutes, we encounter the same profound truth. Time is relative. Time is constructed. Time is a mystery that connects the largest scales of the cosmos to the intimate workings of consciousness. As we close this journey, I invite you to sit with that mystery. Think about your own experience of time. Notice how it varies with mood and attention. Remember your dreams and how time seemed to behave in them. Look up at the night sky and imagine the vast scales of space-time stretching across billions of light years. Contemplate the fact that time itself, that most familiar aspect of existence, is among the universe's deepest enigmas. The universe keeps revealing itself to be stranger and more wonderful than we imagined. From Einstein's revolution in understanding space-time to modern neuroscience's insights into consciousness, we keep discovering that reality has depths beyond what everyday perception reveals. Time, which seems so simple, so obvious, so well understood, turns out to be one of the deepest mysteries of all. And that mystery is worth celebrating. It reminds us that we don't have all the answers, that there's always more to discover, that the universe still has secrets to reveal. Whether you're a physicist studying relativity, a neuroscientist studying sleep and dreams, or simply a person experiencing moments flowing by, you're engaging with one of existence's fundamental puzzles. So, the next time you drift off to sleep and find yourself in a dream, remember that you're entering a space where your brain constructs time in its own way, where the usual rules become flexible, where subjective experience departs from objective measurement. And when you wake and look at the clock, remember that clock itself is measuring something relative, context-dependent, something that would tick differently if it were moving faster or closer to a massive object. Time surrounds us, flows through us, constitutes us, and yet it remains profoundly mysterious. That's the beauty of it. That's why we keep exploring, keep questioning, keep trying to understand. Because reality, when we look closely, is always stranger and more marvelous than we expect. Time, in all its forms, from cosmic to conscious, from physical to experiential, from objective to subjective, embodies that strangeness and that marvel. And thank you for joining me on this journey through space-time and dream-time, through relativity and consciousness, through the physics of the very large and the neuroscience of the very personal. If you enjoyed this exploration, if it sparked your curiosity or changed how you think about time, I'd love to hear from you. Please leave a like on this video, subscribe to the channel for more deep dives into the mysteries of the cosmos and consciousness, and share this with anyone who might appreciate a closer look at the nature of time. Until next time, as you move through your days and nights, as you experience time flowing and construct your own temporal reality, remember that you're part of something vast and strange and beautiful. You're a conscious observer embedded in space-time's geometry, creating experiential time from neural time, from physical time, from the deepest structures of reality itself. That's a wonder worth contemplating. Sleep well, dream deeply, and never stop questioning the nature of time.